Hello Year 10, this is the revised version of forces and elasticity. Apologies, the previous video was corrupt. What we're going to do today is go back through this and hopefully without any glitches. So there is a required practical associated with today's lesson, and what I want to be able to do is go through that step by step so you understand how to do it. Obviously when you're back in school we'll be able to do some of these required practicals and ensure that you've all understood what's going on. If you want to follow this in the Caboodle textbook, then please have a look at the page numbers below. Today we're doing forces and elasticity, and that's page 130 to 131. So quick quiz, 1 to 5 in your margin, and you're going to just pause the slide now and answer the following questions. So the two components that make up stopping distance are thinking time and braking distance. Given the formula for calculating weight equals mass times gravitational strength. What is the resultant force when the object has reached constant velocity and the frictional force is equal to its weight? The resultant force is equal to 0. Calculate the required force to move 100 kilograms across a room at a speed of acceleration of 5 meters per second. And that is 100 times 5 equals 500 newtons. Calculate the acceleration of an object of mass 5 kilograms acted on by a force of 40 newtons. And again, that's 40 divided by 5 equals 8 meters per second squared. Now, there is a link that's attached to this video. And if you watch this link and then think about the physics behind it for me, and then you can move forward. I've pasted this in the bottom. What forces are acting on the bungee jumper? Okay, so if you're aiming for a grade 4, you need to know that you need to be able to label the forces quite simply. What do you need to know to make the bungee cord the right length for it to be safe? Now, obviously, you don't want the length to be too long that the person then hits the floor, okay, and breaks their neck, because that would just not be a good thing to be happening. The other thing is a lot of these occur over water, so they can just end up in the water and drown. And that is a common accident with these. So this is why they need to know certain key pieces of information before we start. What energy transfers are taking place? So now we're linking forces to energy, and that's really important because that is the link pushing us above a 6 for the 7, 8 and 9 is linking those energies to forces. So here are what we need to know. I suggest you pause the slide and write down things that you didn't know rather than just copying it all down. And it also gives you the explanation in relation to Hooke's law. Now, Hooke is a physicist that we're going to be coming up to in a minute, and he was very famous for lots of things. However, Hooke's law was very important for using calculations, and we need to know certain pieces of information about the material that we're using as a bungee, okay, whether it's the elastic limit, the recoil, and the weight of the jumper. So here's Hooke with his awesome hair. Yes, there he is, looking very dapper in his cravat. So his idea, Hooke's law, is basically this concept that the extension of an object, so how much it stretches, is directly proportional to the force applied to it. Now, this is assuming that the material that we're using is elastic. If it's a plastic material, okay, one that doesn't stretch necessarily, then what we then see is non-elastic deformation. So put that bit in bold in a box so that you've got it, okay, here, because it's something that comes up time and time again in the exams. So you need to know some key pieces of information. So this is the equation that you need to know to be able to answer the questions. And here we've got that force is equal to spring constant, and that could be the same as our rope. It doesn't necessarily have to be a spring, times extension. Spring constant is a K, so be careful with that one, because sometimes they just put F equals K times E, and people are like, well, what's the K? I have no idea. So think about, what are the units? So my units, forces are always measured in newtons, capital N, because it's named after the man. And spring constant is newtons per metre, and extension is metres. Therefore, we can then use that information to answer some other questions. Now, again, we've got this idea of proportionality, and we've got 4 graphs here that you need to be able to learn, explain what they're showing. And this is similar in all 3 sciences. It's not necessarily a physics explanation here. This is a scientific explanation. So if I just pause the slide, sketch these 4 graphs out, and decide which definition goes with which graph, okay? So, yeah, thanks. So, directly proportional, that is graph B, okay? And we can say that it's directly proportional because if one variable increases, so does the other. We can see that this is true because it's a nice straight line, and it's moving away from the origin up to the top right-hand corner. There's 0 correlation. Now that's C, because that looks a bit like a chickenpox pattern on the page. It doesn't really show me any correlation. There's no clusters, and therefore we wouldn't be able to put a line of best fit on that. Inversely proportional, and that will be A. So as one factor increases, the other decreases. This can be a straight line, or it can be a curve. Just be aware of that. And then a linear relationship, and that's graph D. And as you can see, that it's a straight line going straight through, but it doesn't start at the origin. And here are the answers. Okay, and they're the clear definitions that might be better than my ramblings like a crazy lady. Okay, let's move on. So the required practical, sketch out the equipment, okay, because this is often a 6 marker, and they want you to be able to explain how to do this. So pause the slide and sketch the diagram for me. Brilliant. So what we've got here is we've got a spring, we've got a clamp stand, we've got a ruler, we've got weights or masses, it doesn't matter which way around you call them. And here we've got the original length, and then the extension, and then the total length. So the original length and the extension equal the length, okay? And what we need to think about is, what is our independent variable and what is our dependent variable, and what will you keep the same? Now, ideally, things that we keep the same are called our control variables, and we would use the same spring throughout. That's really important because the spring has a constant, and therefore we need to make sure that we're using the same spring. If you swap springs halfway through, it would stretch different amounts. The independent variable, and things that we're deliberately changing, is the weights that we're adding to it. And we would add the weight and then measure the extension. To ensure that this is a fair test and we hadn't overstretched the spring, what we would do between adding each weight is take off the weights and ensure that the spring returns to its original length. If it doesn't, then it has gone past its elastic limit, or its limit of proportionality. The dependent variable is the thing we're measuring, okay, and that's the thing we're measuring as a result of adding our independent variable, and that is the extension of the spring. And the things that we're going to keep the same, we're going to keep the spring the same. We are going to measure from the same point on the spring each time. Sometimes we can add a little post-it note. Sometimes we measure from the bottom of the ring or the bottom of the actual spring. Doesn't matter which one we do, as long as we do the same thing each time. And also another one, especially if you're using a really stiff spring, is allow the spring enough time to extend. Okay, so leave it for 30 seconds before measuring the length, and also maybe stop it bouncing up and down, which can be quite tricky, especially some of the cheaper springs. And what will the results table need to look like? So just as we always do, the independent variable goes in the first column, okay? And that is just the key thing that you should be remembering now. And so in that first column, we've got the weight in newtons. And then we've got the average length of the stretch spring, the original length of the spring, and then the extension. And that's what our results table should look like. And we need to take a minimum of 5 readings for it to be reliable. And we also need to make sure it's repeatable, so therefore we want to ensure that we repeat this 3 times with 3 different springs, preferably with the same spring constant. Or you can use the same spring, doesn't matter. So here's the stretch test video, exciting stuff as it is. Watch the video. This is somebody doing the experiment and you can see how it would be done. You're not missing much, guys. It's somebody putting weights on a spring, but it's exciting, especially if you like physics. So you need to consider a mass on a spring. And we need to think what happens when the masses are added. So when the mass is added, that is a force and the spring will change shape and extend. Now, find an expression that relates extension to the amount of weight added. And that is our expression. You do need to learn this equation. It's not given to you in the exam. Using the information from the video, work out your spring constant. And then we would need to draw a graph. Now, you may not have graph paper. However, what you should see is something like this. Even if you sketch it out on your line paper, don't forget, if you've run out of space in your book, email me and I will pop one in the post for you. And I can even put in some graph paper if needed. So what we can see is this first part of the graph here is nice and straight. We'd say that's directly proportional. And then once it starts to curve round here, we say it's reached its limit of proportionality, or it's its elastic limit. And they're really important, okay? They are really, really important. Now, if you put too much force on the spring, it stretches. In other words, you remove the force and the spring does not go back to its original length. And as I've already mentioned, this is called inelastic deformation. If you do not use too much force on the spring, you can take the force off and the spring returns to its original shape. And this is elastic deformation. So think about forces and compressions. We've looked at forces and stretching, but forces and compressions have the same principles. And this is just the same as the suspension inside your cars. Okay, these are some suspension springs. So the force compression graphs for objects like this can be determined and plotted. So have a go at these questions for me. And here are the answers. So elastic potential energy. So by adding the force to the spring and stretching the spring then basically gains potential energy. All right, again, looking back at my spring, when we add the mass, it stretches downwards. If I take the mass off, it recoils. And the reason it recoils is because it has elastic potential energy. So when a force is applied to the spring, it will change shape and extend. And that's when the energy is stored. Okay? And that stored energy is elastic potential energy. Okay, have a go at doing these 5 questions for me. Pause the slide and answer the following. I'm going to quickly put up the answers and you can mark your own work. Okay, give yourself a mark out of 5. And if you haven't got the answers correct, show the workings as we've done on the slides. Thank you. The key points from today's lesson. An object is called elastic if it returns to its original shape after removing the force and deforming it. The extension is the difference between length of the object and original length. The extension of a spring is directly proportional to the force applied to it, as long as the limit of proportionality is not exceeded, so we haven't stretched it too far. This relationship is linear, that means it's a nice straight line. And beyond the limit of proportionality, the extension of the spring is no longer proportional to the applied force. This relationship becomes non-linear.